Good. So let's go back to this morning discussion. And I was at a point where somehow we identified three key objects in what we would like to term quantum mechanics, at least for our mathematical and quite abstract point of view. Okay, this is what you cannot do without. Okay, so in any formulation you could identify something which resembles to this object. So this is an algebra of observable, which we took being inside a sister algebra as the set of self-adjoint element of this sister algebra. And yeah, so what is the difference? Well, it's like complex number. Okay, you either have all the complex number, but of course you only care about real numbers. Okay, so the real numbers are inside the complex number as self-adjoint elements. Okay, that's not more than this. The additional structure is important, okay, but somehow the object you are interested in are the self-adjoint elements, okay, like in real world, okay, you're interested in real numbers, but the structure of the complex number, it somehow encodes some of the properties of that you care about. Then we have a state which should, so the observable somehow is the experimenter who chooses what observable to observe. So this is the experimental setup. Then you have the nature on the other side. Then the nature chooses the state of the system. Okay, and this is a linear functional on the observables. So you have this duality. You have two players and they come together and produce a number, which is the measurement you observe. Okay. And there is a very nice duality in the theory of sister algebra between state and observable, which somehow make a very compelling model of that. Okay, so somehow it could seem a bit abstract why we take the sister algebra. Sister algebra are quite rigid objects. Okay, so it seemed, I mean, as far as we know, there is no reason why we should use sister algebra, but give a very nice modeling. And then we have this automorphisms group. So this is a mapping from the sister algebra into itself, which preserve all the structure of the sister algebra and which implement the time translation. Okay, and again, okay, it's a bit difficult to think if you try to think about points and about classical, with a classical intuition. There is no point moving in space as in classical dynamics, but you follow the evolution of the observables. Okay, in classical dynamics, you can follow the evolution of functions. Okay, this is very common point of view in dynamical system. Okay, you look at space, and then you have space of functions, and then you can define, if you know how the points move, then you can also, you know also how function moves around, okay, change with the time. And this is all it's written here, okay, essentially. And any other so this is like a time symmetry of the system, okay, the system remain itself, in a sense that the set of state does not change, okay, a classical system does not, okay, a system evolving in Rn does not become a system evolving in Rm after some time, okay? So you take a space large enough which encode all the evolution of the system, so this is give you an automorphism of the algebra of the observable, and then other symmetries act in the similar way. And then the main problem of quantum mechanics that you want to compute quantities, which then you can compare to experiment, and this is essentially, you want to select some observable and at different times, and then try to compute these quantities. Okay, and the idea is that, okay, what happens in this abstract framework, you cannot do very much because somehow at this point you would like to choose coordinates, and as we have seen by the Gns construction, you can obtain coordinates which somehow associated to any state. Okay. Now let's be more precise. So we need so I want to arrive at a point where we have a concrete example. Okay, so it will not be right away. You can look at the material I suggested you in the first lecture if you want to see examples. I want to arrive at a very specific example which is useful later on, which is the harmonic oscillator essentially. But okay, we still need some more material. So the one of the things is that so the dynamics acts on the observable, but by duality can act also on state. Okay, so dynamics acts on states by duality. But that is quite, I think it's quite clear. If you have a state and you have an observable, you can define a new state, okay, by saying, okay, the state at time t, if you want, the state translated time t, by saying, okay, this new state is just the old state where I just transformed all the observable, okay? So this is by duality. Okay, I use the same symbol. It's like the dual, okay? And then in general, so what does it mean? That remember that for every state you have a new Hilbert space, okay? But the interesting situation, and a priori the representation could be irreducible, okay? There is no reason a priori all the states should have the same representation. Sorry, in equivalent, okay, at different time. But essentially, if we want to continue and have nice construction, so for example, in the scope of this lecture, just to have an easy example, because essentially I don't understand what happens if the following condition does not hold, we will assume, okay, that this will contain the many example we want to consider, okay, that we have an invariant state, let's say omega at our disposal, okay? So I want to have a state which does not depend on time. Okay, so this is essentially this describe, so what does it mean? Describe a quantum system which does not evolve, okay, in itself. Is not, that is not, so this will allow me to do a construction. Then of course I can access other states, okay, because for example, just to go back in the discussion of this morning, okay, given a state, you have an Hilbert space, and then all the vectors in this Hilbert space are pure states, okay? So now a state fixes a representation, but inside this representation there are other states, okay? Actually, then you can define a notion of volume. We will not need it, but somehow is all the state which you can access with the representation which generate representation unitarily equivalent to the given state, okay, associated to the given state, let's say. But okay, we don't need all this specificity here. Just let's take this assumption, because this then will allow us to construct sorry, yes, this will allow us okay, let me just be brief here. I don't want to spend too much time on this point. So this will essentially identify a representation. So let me say in this way. What will happen in this situation? Of course, the state does not move, but you still have you still have an action of the automorphism algebra. Okay, so in this case, the group alpha, okay, generates. So you see you have a representation. Okay, so let me. Okay, in this case, you have the representation. Then you can ask, okay, where it is send an a specific observable or a specific element of the sister algebra through when you apply the automorphism and with the representation associated to this state. Okay, and then what will happen? You can find out that actually all these things are for different time are equivalent, unitarily equivalent to each other. So there should exist a unitary map, which let me write in this way. There is a one parameter group of unitary operators. So in the Hilbert space, so you have a one parameter group of unitary operator in the Hilbert space H omega. So now somehow I fix a state which is invariant. Okay, I hope to have one in the problem I need to solve. I discovered myself with much surprise that whenever this is not the case, it's quite difficult to proceed in this approach. Okay, but essentially the case we are interested in this class. There is a discussion in the book of Strock about this point. So in this case, somehow this representation I think I need yeah, okay. Somehow the point is that you can put yourself in the situation where you can have a one parameter group of unitary operator which acts in the Hilbert space and which implements essentially the automorphism group. Okay, and we assume that they are strongly continuous. Okay, so this is the standard setting. If you don't have these assumptions or if you don't have these properties, it's then quite difficult to proceed. Okay, this is very mild because somehow it's enough for unitary operator. It's enough to ask weak continuity to get strong continuity because they're bounded. Okay, continuous. Okay, so this is the setting. And at this point, we have reduced, so the fact that the state invariant somehow allows you to work in a given Hilbert space with a given vector, ground state vector phi, okay? So we consider the Gns representation given by h of omega, pi of omega, this is and the state phi of omega, okay? And then the dynamics in this case, it's given by this unitary family of operator of unitary group, which you assume that they are weakly continuous. Okay, this is a regularity property we associate with the dynamics. Okay, so now we have reduced. So now from here, I'm trying to proceed. I'm trying to make a series of assumptions which allows us to have a concrete representation of these objects, which will are the object of interest for us. Okay, so in particular, we have a formula. Okay, so in particular, let me know if the font is too small. Maybe I can have even a bigger font for the slide. Would be better. Okay. Okay. Now we have represented. We can be more explicit. Sorry. we can be more explicit in our representation of the right-hand side. Okay. For example, okay, I will restrict sequence of time to be increasing in this sense, for example. And okay, you can even take that, that's not a problem. And then you want to, so this was our initial problem. I want to represent this, this measurement, the result of this measurement. Then with these assumptions, you can write it in this way. Okay, so I hope, of course, yeah, I hope I did it correctly. I don't, yeah, I could have, let me see, t is negative, so I think I should write in the opposite direction. I don't, it's not very important, just it's probable I got it wrong, but I mean. Okay, because essentially when the U act on the vacuum, this is 0. Yeah, this is another, since the state is invariant and the state generates this vector is also invariant. Okay, so you have this kind of relation. And then the observable, they change in a unitary, they are conjugated by the flow, by the unitary group. Okay, so now you are in a situation like this. Okay, I can represent this concretely in this way. So the operator at there is no U here on there because they are unitary and the state is invariant, so they disappear. If the state is not invariant, they don't disappear and things get more complicated. But in this case, you see that first observation, these functions depends only on the difference between times. Okay. So we say they are time invariant. So we are, I don't know, time, yeah, translation, yeah, time, yeah, something like this. So this correlation, these are correlations, okay? So these correlation functions, so they somehow tells you what happens when you measure things at different times, and then they depend only on the difference of the time. This is because somehow the state we are looking at does not care about the origin of time. Okay, the dynamics does not change the time. Okay, so the only things you can see is what happens between two different times. Okay, and now the point is, yeah, now you have to, so now somehow this should be all that it's needed. And it's natural to make the following hypothesis. One says, so there is a notion of cyclic, again, okay, I don't want to be too precise because this would require, is such phi omega unique? Yeah, that's unique up to a complex number. Okay, so this is determined in a unique way by this GNS. I didn't prove the GNS construction, okay, but essentially, the only thing that you see that it appears only always paired with in this kind of expression. Okay, so if you multiply by a complex number, you get the same thing. So it's not unique in this sense, but otherwise, and actually, sorry, let me say you don't. So in the construction is unique because the construction gives you one object. Then it depends in which sense you mean that it's unique. So probably in any sense you would like to think about it is not unique, but you don't care. So you see the objects of this representation, you can representation, yeah, I'm not sure what you mean by unique. So in the same Hilbert space, there is only this vector which do the job, I think. But the question of uniqueness does not enter this. does not enter the issue at the moment. Okay, there is no issue about uniqueness. It's a convenient construction. Okay, so just exists. Maybe there are other unitary equivalent triplet. You can change Hilbert space. You can change vector. Maybe in the same Hilbert space there is another vector which has this property, provided you do an unitary transformation. But the point is that you don't care about each of objects separately. You only care about them all together. That's would be my thanks. So somehow that's like, it's like a choice of a coordinate system. Okay, if it's unique or not, you don't care. Probably it's not unique. Okay, there is another coordinate system as soon as you make a rotation. That's not the problem. It's a choice. Somehow the structure guarantee you is that whatever choice you make, you get the same number at the end. That's the only thing you care. I think that's the right way to look. Okay, there is never if you want, all the countably Hilbert space are equivalent. The point is not is how the various things you construct on the Hilbert space are related to one another. Okay, it's not the space itself which has some particular meaning in this context. Okay, and I like this approach somehow because it shows you how the Hilbert space is generated, and that's the point. Okay, you need another condition, but it's always somehow you are always you said that this state is cyclic, so this vector is cyclic, or the state, whatever, if the span of the vectors. So somehow this is the important vectors of the form. Of this form, So now, sorry, I'm using, probably I need to use the other. Okay. So now what you do, okay, you check the following property, okay, you take this vector, which was generated by the Gns representation, and then all the operator which represent the algebra in this Hilbert space, and all the unitaries, because you have the dynamics, and you create all the possible objects algebraically that you can, okay, you sandwich operators, the unitary group between two times operator, and so forth. Okay, and then okay, this generates a large class of vectors, and then you ask, that's the question you want to ask, is that can I reach every other vector in the Hilbert space in this way? Okay, can I generate any other essentially pure state in this way? Okay, that's somehow the question you ask, and you say that the vector is cyclic in this case. Yeah, so this is an important property in this kind of formalization. Okay, whether you can represent everything in terms of operation applied to this particular vector, which is given to you by the Gns representation, and that's the situation you would like to be, because somehow provided you have this, you can reconstruct everything from the value of these numbers. Okay, so I gave a name to these functions. I call it W because somehow they correspond to the Weitman function in quantum field theory, but okay, you just can, okay, this function, it's a very large family of functions. Okay, you can select time, you can select operators. Actually, let me call small r. So the big R just the representative of the small r. Okay, just to be clear. And then I'm not sure I wrote it somewhere. Okay, with let's say big AK is pi omega AK. Okay. So all these objects, provided this is the case, all the correlation functions in this form form a complete description of the dynamic. Okay, that is allowed to reconstruct your data, okay? And also you, okay, the unitary group. Okay, so that's maybe a first point I want to make. So let me, so this is another point, important point, okay? So you want to trade, okay, these are families, these are functions, okay? And it's very, so somehow it's like the moments of probability distribution, okay? And then you would like to say the probability distribution is characterized by all the family of all its moments. Here are all the finite dimensional distribution, okay? And the Gns representation does that for you, okay? You can make this analogy, you can push this analogy to say that provided I know all the possible object of this form, all this number for any choice of times and observables, and actually elements of the sister algebra, I think it's enough the observables. You can make any element by summing observables, okay? Then you can reconstruct the quantum mechanical data and you can essentially reconstruct all the others. Okay, so somehow you see this family contains, you don't lose information if instead of looking at this object, you look only at this family. That's the message of this black triangle here. Again, okay, in particular, you can reconstruct also the unitary group U, okay? So it's encoded, or at least, yeah, it's encoded inside these numbers, okay? So you can decode somehow the state. Yeah, okay, from this number you can decode all this data separately. Okay, so imagine you are given this function, okay, just to be clear. Then you can decode the state, you can decode the sister algebra, of course you have to know, okay, but the state it's encoded in this family of functions, and also the dynamics is encoded in this family of functions. Okay, so you can reconstruct the Hilbert space, you can reconstruct the Hilbert space, the representation, the ground vector, and the unitary group. And therefore, also you can re-express all the other, okay? And also in the very precise sense that you can approximate certain correlation function with other correlation function. Okay, so this is the first point. This is the structure I wanted to point out so far. And the idea is that we can care about only this called Whiteman function, okay? These are like baby Whiteman function. Baby because, of course, okay, you need to, the proper Whiteman functions are defined for usually for quantum field theory. But let's say to understand the concepts, I find useful to look this in this very simplified setting, okay, where we only have time. Okay, so this is the reconstruction of quantum mechanics from Whiteman functions. This is the first step. Now we want another step, so maybe let's not put number because these are still, so this is one step in our path towards what does it mean Euclidean quantum field theory. Okay, so somehow we have laid out what is quantum mechanics for us. Somehow I try to motivate the fact that one can look at correlation, a function. So these are functions, okay? The interest is that they are very natural, okay, very well-known object. Okay, these are function of times and of a series of index, which seems complicated, but essentially does it mean, okay, choose for me a sequence of elements in the sister algebra, and then I assume that I have the corresponding function. And this hierarchy of function is countable, no? Okay, you start with the one element in one time, or one element 0 time, and then two elements 1 time, and so forth. and then you can construct all them, okay? Somehow by this notion of cyclicity, you see that you reduce the problem to somehow finite dimensional distribution, if you want, okay? You can, it's enough, this vector approximate any other vector in the Hilbert space, so you can approximate any other objects in the Hilbert space in this way, okay, by just applying infinitely many of these objects. So this is the idea, okay? We traded for the quantum mechanical data for these Weitman functions. And now we want to transform this Weitman function in other functions, because these other functions will have a probabilistic interpretation, okay? So what is the goal here? So doing Euclidean, so Euclidean quantum mechanics somehow means, Euclidean quantum mechanics means to do quantum mechanics in imaginary time, okay? So that somehow, it's the intuitive meaning, okay? So what does it mean precisely? Okay, what is imaginary time? Okay, so you go back and actually so why you want to do that we will discover later, okay? But let's say I want to give a precise meaning of this notion to take imaginary time. Somehow one intuition is that so if you think about quantum field theory, you want to deal with the Minkowski metric, but the Minkowski metric is complicated because the signature is plus plus. There is -1, okay? The time has negative signature. And if you take imaginary time, somehow intuitively the quadratic form become positive definite, okay? And is actually the Euclidean quadratic form. So that's why you call it Euclidean quantum mechanics, and why this imaginary time correspond to somehow go into the Euclidean setting. But what does it mean precisely, apart from this heuristic consideration? Is the following. So one can prove in various ways. That's where somehow you could invoke unbounded operators, okay? But you have unitary group, and we assume that it's strongly continuous, okay? So the time intervenes in this formalization only inside the unitary group, okay? So we need to understand what is the unitary group look at imaginary times, okay? So that's a bit the goal. So you go back a moment and you say, okay, if you want by Stochastic theorem, so by so this I want to say in this way, okay? This is what I was saying this morning, that I really don't want to talk about unbounded operators, okay? Not because I mean I want to play this game to say, okay, how far you can go without using this concept. And you can rephrase Stochastic theorem somehow, yeah, without Stochastic theorem is the equivalence of 3 different objects, and you can get rid of one of them, and for us would do fine. And what is this for us? So will be that as soon as you have a strongly continuous unitary group in a Hilbert space, then you have an homomorphism from the algebra, the sister algebra of continuous function, on R into the bounded operator on an Hilbert space, okay? At this point, I fix the Hilbert space, okay? This Hilbert space is fixed because I choose a stationary state, and I've done the Gns construction. So I don't write omega anymore, okay? It will be fixed from now on. Okay, so what does it mean? Okay, so you say, so this means, can you guess what does it mean? Okay, it means that, for example, if you give me a function, if you give me two functions, so homomorphism just tell you that, no? then xf and xg are are bounded operators, and xf time, and I know how to compute the product because essentially it's the product of the functions. Okay, in particular, the product is commutative. Okay, so the image of this homomorphism, it's a commutative subalgebra of the algebra bounded operator, and then the involution works as usual. In particular, you see that if you take the function t of x, which is exponential, the complex exponent. So this is telling, okay, how this is related with the previous, then what it says is that if you compute on this function, you get exactly ut back. Okay, so you have this relation from ut, I can construct this object, and from this object, I can construct ut, okay? So one could write, in various reasons, xf, you could say that f of x is equal to xf, okay? It's a notation. It's a notation. Then one has that f of x times f of y, f of x times g of x, okay, by what I did before is f g of x. Okay, so this is the product of this operator can be computed as product of function. Okay, maybe if you know now the theorem, you recognize it better. Okay. Again, okay, we don't have to discuss unbounded operator in this setting. And even in the proof, you don't really need to go through unbounded operator to prove the theorem in the way I stated here. But then this will give us, okay, now I have to say something about, okay, this, so now I know somehow, you see, I said essentially that via this homomorphism, the unitary group correspond to these exponential functions, okay? So this seems quite easy, because in this exponential function, I could imagine how to take the time to be complex, okay, to be imaginary, okay? I know somehow what does it mean take imaginary time in this exponent. What does it mean to take t equal I tau, okay, imaginary time in et, okay, et of x. That is, okay. If I take e tau of x, what I get? Well, I get what everybody think. Okay, now I don't have, yeah, tau, okay. Now, what is the problem with this function? Okay, but this function, this is a function of x, okay? I have to consider it as a function of x, a given t, okay? I want to take an imaginary time. But this function is not bounded in general, okay? When it's bounded, okay, of course, it's the exponential of a product. So when it's bounded, okay, to have it, but why I care about boundedness, okay? I care about boundedness because somehow you see, this is what you allow me to construct is just an homomorphism on bounded functions, okay? So if you're a bit puzzled, let me stop a moment. If you're a bit puzzled about this construction, so just think about, no, if you essentially it's like Fourier transform. Okay, it's a complicated way to do a Fourier transform in this setting. Okay, you know what it's saying. So somehow this is the you can think again. Okay, probabilistically. Okay, this is the characteristic function of this homomorphism. Okay, that is, if you give me a homomorphism of this sort, and I compute it on this exponential, then I obtain a one parameter semigroup. That's somehow exercise for you to check that this is a one parameter unitary group. Okay, so exercise if you want. check that. Okay, if you have a homomorphism, this is a unitary. Okay, yeah, to have the weak continuity, you have to be a bit careful, but that's the case. But just check algebraically that this is a unitary group, okay? Because you see it's a homomorphism. So when you multiply the exponential, you get what you expect, okay? And you can construct the inverse just in this way, okay? Just mapping. Okay, so I can take this, but this function is not. So I would need that tau is positive. This I can allow. Okay, let's say tau is positive and x positive. Okay, so in this case, okay, in the domain where tau and x are positive, this is a bounded function, of course. And that's the setting. Okay, so I would need somehow to require that this homomorphism does not look at the value of the function in the negative for x negative, for example. Then I can take tau positive and have a bounded function. So you introduce a concept and you say the group U is of positive energy. So this is the name you gave her this notion. If and only if x of f is 0. So by Stone theorem, you have this correspondence. So for all f with support in x negative. Okay. So every time you give a continuous function which is just supported in negative numbers, then the homomorphism is 0. The homomorphism it's determined by the U. So you say U it's positive if you have this property. Okay, and as soon as you have this property, okay, I have a question. Sorry, I didn't see. Is X defined on continuous or bounded continuous functions? No, yeah, okay, that's a good point to make. Here, is a homomorphism of sister algebras. Okay, so essentially, you have to think that when I write this symbol in this lecture, is always bounded continuous function. Okay, I don't, because somehow this is automatically, if it's a homomorphism for sister algebra, the norm, okay, you need to have that the norm of the function is equal to the norm of the image on the target space. Okay, I told you sister algebra is quite rigid object. Okay, as soon as you have homomorphism, has to be isometric. Okay, so it's bounded functions. Okay, the norm here it's the uniform norm. You cannot use other norms. Okay, that's not, otherwise it's not a sister algebra anymore. Okay, so but thanks for the question is a point. Okay, I think yeah, I could not enter very much into the structure of sister algebra, but I think you have to keep in mind that it's rigid, that there is only one norm, and on continuous function the natural norm is the uniform norm. Okay, there is no other possibility. Okay, so now we start to, if you know the theory of a bounded operator, of course, you recognize what is this in that language is the continuous functional calculus, for example, for a self-adjoint operator. Okay, so to any continuous unit, strongly continuous unitary group, you have a self-adjoint operator, which is unbounded, but if you compose with continuous function, you can define the object and it's a bounded operator. Okay, and somehow the fact that there is in between unbounded operator, you can get rid. Okay, in the formalization, there is at this level does not play any role. Okay, actually it's more compact to think about this as really a Fourier transform. Okay, so you want to look at this kind at this family of functions. Okay, or somehow it's an embedding of an algebra of commutative function into a non-commutative algebra, and you can characterize it via this unitary group. Okay, to every unitary group, there is this homomorphism and vice versa. That's okay. That's quite compact, I think, and I find very compelling. It's like the theory of characteristic functions for this object. Okay, if you know the Fourier transform, you know the function, and vice versa. And that's okay. That's the point. Okay, that U it's of positive energy. Somehow, this whenever you pass to this homomorphism function, which is supported on negative times, then you get 0. And at this point, somehow you can implement what we already said. Okay, so in this case, so let me make this point. In this case, for a positive energy group, one can define, now I can do it. Okay, so now this is, I can compute the homomorphism on the exponential function. Okay, with S positive. Okay, this function is not bounded over all X, but I just cut for R positive, and then you have to put some care, because of course this is not a continuous function, but somehow how you continue in the negative real axis does not matter, because the operator, the homomorphism will not depend on how you continue this function in the negative axis. And then this defines a bounded operator. Okay, so this defined for any time a bounded element of H. And you observe that, again, okay, that you can, it's a homomorphism. So when you compose two of them, you just have the product of the two exponential, then you get the exponential of the sum. It's bounded by 1 and it's strongly continuous. Okay, you can prove that. Okay, so you have, to summarizing, you have a strongly continuous semigroup of contractions. And you can go back, actually. You can go back and obtain a unitary group with positive energy. Yeah, so, okay, we didn't lose, you see, I'm doing a series of transformation, but taking care not to lose information on the way. Okay, so, so trading, so I told you, instead of U, you can consider X. Now I'm telling you, instead of X, you can consider K. Okay, this is like the Laplace. Instead of taking the Fourier transform, you take the Laplace transform. It's okay. You can, under this condition we gave, you can go back. Okay, and now given the, provided you know this operator, then you can reconstruct X and then U. Okay, and essentially they describe the same object. Okay, and this object, it's the dynamic of the quantum system, which I cared about, but described in a different way. Okay, so since they contain the same information, now I can introduce a further object then, which okay, so they contain the same information. So if I know how this operator acts on the Hilbert space, then essentially I know how you acted on the Hilbert space. Okay, so I go back. If I knew how you acted, I can essentially construct this function somehow. Okay, so the knowledge of the action of the U in like things like this, so the knowledge of this W function is equivalent to the knowledge of other functions, in which you replace U by K, okay, because somehow they contain the same energy. Okay, so provided the dynamics has positive energy, again, this is assumption. So we are making a series of assumptions along the way, but somehow they are the assumption for which we can construct example. Okay, then I can consider this operator. You see, I can consider these other functions. Okay, again, as before. Okay, you consider positive times and you consider these functions. Okay, I can do it. Why not? And now the question is always, okay, given these functions, can I go back and recover the data of my problem? And that's okay. Can I go back? Okay, from S to W to whatever, to, I didn't give a name, but okay, essentially Hilbert space. representation, state, dynamics. Okay, unitary group if you want, or dynamics is the same. We call this, sorry, we call this Schwinger function. That's why I use Schwinger functions. Okay. Okay, now start to be more interesting. Okay, so now we have this question, okay? You give me all these functions, can I recover the data? And this is where reflection positivity enters. Now, let's consider is it clear, the problem? Do you have a question? Maybe I lost you at some point at this level. I want to be sure that we are on the same page. Okay, the idea is that we have, this is a bunch of function, okay? Function of times, let's say, and okay, operators, whatever. And we are asking, okay, if you give me all this function, can I really have a construction which give me back the Hilbert space and everything, or some isomorphic version of this data? And the basic idea under all this reconstruction is really this Gns theorem, which you can find even in the lecture note, in the book of Stroke. I think it's very interesting to see the proof. I don't have very much time to prove it. I just want to, and here is the same. So now you see what you want to do, you have to construct an Hilbert space. So somewhere in these functions, okay, somewhere inside the family S, okay, of functions, there exists the information of the scalar product, okay, for example. There are various informations, okay, scalar product in the Hilbert space. Why? What I'm saying, okay? Let me give you an example, okay? Consider, for example, this function. Let's take a concrete example, okay? So it's a special function, okay? But you take this specific combination, okay? You take three different operators, a 1, a 2, a 3, and then you take these times, okay? And this function, according to this definition, should corresponds, okay? If we have the quantum problem, we get the functions, okay? Then you have to imagine that there is no quantum problem and you want to go back. So, but okay, let's say that they come. It's easier to understand that I have the quantum problem and I construct the function. So what I know about this function. Now you look exactly why I choose this particular combination is because you have on this side, you have this, and you have exactly the Hermitian conjugate here. Okay, let me maybe not assume that these are self-adjoint elements. So for example, here you have to take the adjoint to have what I am saying. And then in this case, you have all the adjoints, and then the semigroup K is self-adjoint. Okay, this you can check by yourself, okay, because it's a map of a real valued function, so it's self-adjoint. Then you know that, okay, this is, what is this? Well, this is just the scalar product of a vector with itself, so it has to be positive. Okay, so you see that inside all this big family of function, there are the information that they are coming from a scalar product, okay? Because, for example, this function has to be positive for any choice you can make of this parameter. Okay? If it's not the case, it's clear that these functions are not coming from an expression like this, okay? So you just have to stop at that point to worry about reconstructing. And of course, you have other, okay, and many other relations like this. I don't bother to write them all because, okay, you can write the general form. Okay, now you understood the trick. Okay, you take vectors. We assume that they are, okay, for you they are cyclic, but it's the same essentially here, because essentially you can approximate the k with the u, and then you can approximate also, therefore, also these are cyclic. And yeah, so you see that somehow this encode all the, so this function encode all the possible scalar product, okay, essentially, okay. The functions S encode approximations of all the possible scalar product. Good, okay, and also encode the fact that K is a semigroup of contraction, okay? Strongly continuous. Strong continuity is important, otherwise you cannot do certain considerations, okay? Especially does not work, okay? Essentially, the strong continuity comes from the weak continuity. So you can imagine very well how you could encode weak continuity by saying that if the parameter converge, if you move some time and then they converge, you get the result, okay? Okay. So this property, okay, so the set of all these properties, positivity, is called reflection positivity. Okay, or Osterwalder-Schrader condition. Now, it's not clear why it's reflection positivity, so let's call it Osterwalder-Schrader positivity. Okay, so that's an important condition. Okay, so somehow that motivates you to look at family of Schwinger function which satisfy this property, because you know that only, okay, the only Schwinger function which come from, only the function which come from Hilbert space representation, they can satisfy this property. I didn't want to introduce, there are axioms you can check, you can look in the book of Berry-Simon, so good references, for example, for all this matter, it's the book of, so let me write some references for this section. Certainly there is the book of Berry-Simon, which is this book. You have more detail, and there is the book of Klimenjev, of course. This one. Oh, sorry. And I would say there is also a very nice paper of Epstein, just to see how does it work. Okay, but then things are, yeah, okay. Yeah, maybe that's okay. Let me just cut these two books, okay, if you want to understand more in detail what's going on. And again, to the lecture note of the course, okay, we gave in Bonn last semester. Okay. Yeah, sorry, I was. was thinking, yeah, just I want, okay. There are three conditions. Essentially, there is a theorem, then a reconstruction theorem. Okay, let's say baby version, I say, because we don't introduce all the other details, which somehow I think this is the message I want you to take back, is that if you give me a family of Schwinger function, provided these functions, so actually satisfy three properties, okay? And these three properties, okay, let's name here. So the first property is reflection positivity. Again, okay, I would never write it down exactly what does it mean, this property, but is this property I try to illustrate you here in this example, okay? It's somehow certain linear combination have to be positive, okay? So this is reflection positivity. And you can write it down in detail what they are, okay? That's not the point here, okay? Unless you don't want to prove anything, it's not very insightful to look at them, okay? Then some compatibility condition. For example, encoding the fact that K is a semigroup. Now you have to understand that, you see, the fact that you think this expression to come from something like this means that there should be some relation between different functions, okay? This is like compatibility condition when you is exactly like in probability theory, when you look at finite dimensional distribution and the family of all the finite dimensional distribution, they have to have some compatibility condition, okay? For example, if one of these variables is 1, then somehow there is nothing here. This 2k, the 2k on the sides, they just compose to make a k with the sum of the argument. So this gives you a lower order Schwinger function. And then you have to be able that all the value you assign to this Schwinger function are compatible in this sense. Okay, so and other algebraic conditions. Okay, which I would say natural. They somehow you need to have the trace of the algebraic condition in the of what you want to obtain in the Schwinger functions. Otherwise, it's not the case. Again, like in probability theory, okay, if you give me just an arbitrary family of joint probability distribution which is not consistent, I cannot reconstruct a full distribution for which all these are just projections. Okay, so you need this compatibility condition in a very natural way. And then there is a third condition, which is an analytic condition. Which encode essentially the contractivity of the semigroup, okay? Plus other constraint, analytic constraint, which I don't want to discuss, okay? But somehow, you see the fact that K is a semigroup is an algebraic condition, but that is contractive semigroup, that is it has norm less than 1, then you have to encode in another way. It's not an algebraic property. And this is somehow related to certain group property of the Schwinger functions. Okay, I don't want very much to discuss how they look like. Okay, so, but let me say an example of analytic condition is something like, I don't want really very much to spend much time here on that, but just to have an idea. Okay, you need to require things like this. Okay, like okay, I take one Schwinger function, then I integrate with the functions, test functions. Then I need to be able to bound with a constant which depends on k, and somehow the supremum. You see, it's a very strange condition, but somehow it says that it's something related to the Laplace transform. Okay, you need to take this function g, then integrate with take the Laplace transform, and then take the supremum on R plus, and you need to be able to bound this by that. If you cannot do that, then you cannot somehow prove the contractivity of the semigroup. Anyway, it's not very important. Okay, just there is a way to encode the information about the operators in the Hilbert space in the analytic properties of this Schwinger function. Sorry, these are the norm in the sister algebra. Okay, so just to be clear, so this is indexed by element in the sister algebra. So you don't need to know the Hilbert space. Okay, you have this element, you have defined a sister algebra, so you know what is the norm. This is independent of the Hilbert space. This is also independent of the Hilbert space, and you need this condition. Okay, provided you have. So this is the statement of Oersted-Schrader reconstruction theorem. I don't want to state it precisely, but if you want, okay, let me. Yeah, so you can reconstruct these Weidmann functions, and then from them it's quite easy to reconstruct the Hilbert space. Okay, that's why I didn't insist very much. So let me write the theorem. Okay, so also the reconstruction. Okay, so if you want a theorem, here's a theorem. Okay, something like this. Okay, so we have more okay, yeah. So we have these three conditions to care about, and I somehow try to motivate each of them. I think this is quite easy. Reflection positivity, encode the scalar product. If you want encode the geometry of the Hilbert space. Okay, because it encodes the scalar product. So the compatibility encodes the structure of also the Hilbert space, and this analytic condition encodes the fact that you have the algebraic structure of the operators, and this the contractivity of the semigroup, which is important because you need to be able to reconstruct a contractive semigroup. And then I go back. Okay, this is why it's important to have a contractive semigroup, because otherwise you cannot invert this relation. Okay, so somehow the relation is that once you have a contractive semigroup, you can reconstruct the homomorphism and then the group U. If you don't have given a contractive, if you want, strongly continuous contractive semigroup. Okay, so you need all these conditions, then you can reconstruct the homomorphism and the unitary group U, which give the dynamics. Okay, so that's why it's important for us to keep track of contractivity. So I go back to my good. Okay, so we are at a point, okay, functions satisfying these properties. Are called Schwinger function. Okay, so maybe so we can conclude that the problem, okay, let me use my fancy framing, okay, so that we see that it's an important point. And we have this situation where the construction of interesting quantum, so we are at a point where we have reduced our problem of constructing examples of quantum mechanics to that of finding Schwinger functions, okay? If I find functions like this, essentially I can go back along all my line of reasoning and construct expectation values of observables. Okay, so I didn't lose any information, any structure. I preserved the structure, just modified the problem, and analytically looks quite different. And I'm at this level of Schwinger function, and this is what it's called Euclidean quantum mechanics. Okay, because somehow I work in a setting where the dynamics is not encoded by a unitary group, but by a contraction semigroup. And that was the result of changing time to imaginary time. Now, what is remarkable, okay, at this point you note, okay, can I construct, why I've done all this effort is really worth the trouble. And then you make, it was made like in the 60s, in the 70s, 50s, 60s, particular discovery that if you go in the Euclidean setting, then somehow your problem becomes a problem of probability theory. Why? Because it's remarkable fact, if you want, this was observed by Nelson, Zimanzik, certainly, and maybe others. I'm not very good. This history is full of people, so let me just put this to names. That correlation function of certain probabilistic, if you want, a good account is of course in the book of Simon and in Glim and Jaff. Okay, I'm not really in position right now to give you a complete account on this matter. So let me just put down two names. Certainly Nelson and Zimanzik were aware of this connection, that correlation function of certain probabilistic model are Schwinger functions. Okay, so that is all these things happens for a probabilistic model. Okay, this has nothing to do with our discussion at the beginning that if you take a commutative sister algebra, you get a probabilistic model. Okay, even in a non-commutative setting, you get a probabilistic model under certain in a certain condition and certain models. So let me, and I want to do this, I want to illustrate in the simplest case where I have 1 degree of freedom, okay? In the sense there exists, so what does it mean? 1 degree of freedom. Somehow there is only one observable which allow me to generate all the dynamics. Okay, I can consider essentially only one observable, and remember at the beginning I'm allowed also to consider any function of these observables. But somehow, if I consider only one observable, it generates naturally a commutative algebra, okay, by all the functions of this observable, for example. There exists. So actually, when you say I have an observable, you really are saying I have an homeomorphism. Okay, so there is a homeomorphism Q. I call Q. So this language. Yeah, let's say I have the sister algebra is given. Yeah, I can single. So let me. Yeah, let me actually. Okay, a particular. Okay, let me say commutative subalgebra. Let me say in this way, okay? Maybe it's more precise. So I have, inside the algebra of all observable, I have a commutative subalgebra isomorphic to C of R. Okay, so this is maybe the good way to decide. Okay, I have C of R. I single out one observable, and this means really a class of functions. So okay, we are okay. I think at this point it's okay. So we can. So since it's isomorphic, essentially, just I can index. So I can identify it with its element, with elements are in C of R. Okay, and on my algebra. Okay, so I imagine that I have a way to embed continuous function into my algebra of observables. Okay, the point is that there are other things around which do not commute, but at least all these continuous functions, they commute among themselves. And then, so in this case, somehow, then you imagine that all the observable I care about, I use to construct the Zwinger function, are in A. Okay, I will use only these observable to construct Zwinger function. Okay, so, and we will assume, moreover, that whenever, so this is my assumption, okay? I want to construct Zwinger function. I just look at this particular subalgebra, and then I have the problem, okay, to give a value, every Zwinger function. Yeah, so you want to construct the family of all the Zwinger function, and you assume that somehow you can represent this Zwinger function as expectation values. Okay, that's the assumption of a stochastic process. Okay, so now we are in maybe, yeah, I'm not sure if we got lost at some point, but that's a point where you see probability appearing. Where X is, so now this is my assumption, okay? I will assume that there exists a stochastic process, real valued stochastic process. Okay, so you gave me a family of continuous functions. So Zwinger functions are indexed by these continuous functions, okay, bounded continuous function. Then you give me some of them, you give me some times, and then I have on my side a stochastic process, and I compute numbers in this way. Okay, so I compute the stochastic process at time t, and then a sequence of time which correspond to increments given by this t, small t. Okay, and then of course, okay, I have to require something about it. That is, for example, in order this not to depend on big T, because there is no big T on the right hand side, I have to require that the process is stationary in time. Okay, that is when you translate the process, you get the same law. Okay, so this does not depend on big T, and actually depend only on these times here. Okay, and you could take big T's there. Okay, we can take, if you in the above definition. Okay. So that's an assumption, okay? That's a wish I have, okay? Can I construct Zwinger function which using a stochastic process? And I mean, the answer is yes. Okay, in the Zwinger's function, there is no indication of the non-commutativity in the way that you can do it in this way. Okay, and here I've chosen a particular case where I have only 1 degree of freedom. Okay, and you see this 1 degree of freedom in the fact that the functions I'm considering are valued in R. So at a given time, my physical system corresponds to only one physical quantity, which is a real number. And I can measure any function of this real number, okay? The square root, the sinus of this real number, whatever, okay? That's at a given time. But then I have the time translation operator, and this moves my, so there is the dynamic, and then even if I consider this very small algebra which is commutative, because at one time I can only measure 1 degree of freedom, so it's a commutative algebra. The fact that I can translate in time and use the dynamic produce somehow other elements in the bigger algebra, because the dynamic automorphism is an automorphism of the bigger algebra, not of the small algebra A prime. And therefore, even if I start from A prime, I can produce other element in the algebra. Okay, and so the Schwinger functions are completely somehow non-obvious. Okay, they are not commutative. Okay, if you look at them as they are defined, but the game I try to play is that I try to find a stochastic process which represent the Schwinger functions. Okay, so this is like a magic mirror. Okay, so here you have the quantum world, and here you have a classical world, and there is a correspondence, but it's not as obvious as you would like to see. There is no ready-made or easy physical interpretation, as far as I know. So the question, okay, so that the question become under which condition on the law of X these Schwinger functions are really Schwinger function. Okay, that is they satisfy yeah, I mean you can reconstruct the semi-group and you can reconstruct the quantum data from them. Okay, and then this was said in the, I go back, so we have this theorem. Okay, if I give you these functions, then you have to check these 3 properties. As soon as these 3 properties are satisfied, you can go back all the way to the quantum problem. So we have to ask for condition. So the first point is that the compatibility condition are easily satisfied. The compatibility condition, okay? It's not difficult condition B. Okay, so the compatibility condition, sorry, I mean this compatibility condition. Let's give a theorem a name. Construction. Compatibility condition in theorem. 2. Okay. Reflection positivity is trickier. Okay, so it's not clear what does it mean from the point of view of stochastic process reflection positivity. And actually it's not clear if any given stochastic process satisfies reflection positivity. So now I need to formulate it properly. We need to formulate in the probabilistic. Okay, so there is reflection positivity for Schwinger function is an algebraic property of the Schwinger function. Okay, certain linear combination, it's positive. Then I need to understand, okay, what does it translate to when I read it on this side, so that I can impose a condition on my stochastic probe. problem. Then the analytic condition is somehow clearer, okay, but that we don't care about it. I think it's more interesting to look at reflection positivity. So, and that's why it's called actually reflection positivity. So Schwinger function is more like Osterwalder-Schrader positivity. So given this process, so on function, so the process, let's say the process live on continuous function for simplicity. Okay, it's not really needed, but just to make a mental picture clearer. So if you give me a function on continuous function from R to R, which I imagine function of the process, you can introduce an operation of time inversion. Okay, that is theta of the function on a path x is f of theta of x, where theta of x is the time reflection of the path x in continuous function. Okay, so this is my stochastic process. Okay. Okay, let's say with trajectories in blah. Okay, just to make simpler, it's not really necessary, but don't want to complicate too much at this point. Okay, so stochastic process has continuous trajectory. The first R is the time, and the second R is the target space, okay, which is one-dimensional. So I take it real valued, just for simplicity. This corresponds to the fact that here I used only 1 degree of freedom. Okay, so my functions here are a function of one real value, but you can generalize very easily to other contexts. Yeah, so I can introduce this time inversion. Okay, I take the path and I just look at it in the reverse direction of time. And then you can check the following, so that for any complex function on, now you look at function only on the positive semi-axis, okay? They look at the positive semi-axis of time. And you take them made in this very simple way, okay? Because somehow they are rich enough to describe any other bounded function, okay? So you take them in such a way that they look, so this is for any x in C, okay? If you want, okay, in C positive, because they look at the process at a given time, tk, and then they take this complex exponential, then you have coefficient, complex and real there, so that you have trigonometric exponential. And very important, this function only look at positive times, okay? So they look at your process at positive times and they give you a number. Then you can check, but I would not do the proof, but essentially this is how reflection positivity looks like. So I go back, okay? Reflection positivity on this side, when you translate as in this expression for these kind of functions, you get this formula. Okay, you get that reflection positivity means that if I take a function like this, and then I take the same function, I reverse the path. Okay. So this function looks only at positive times. Okay, the realization of the path of, sorry, let me maybe be more concrete and just write. Okay, maybe it's more precise to write in this way. Okay, so you have the function and it looks at the path. Okay, if you are in the canonical space, it's exactly the same. But so this function looks only at the positive, what happens in the positive semi-axis, positive time, the future of 0. This function is the same function, but since it looks at the reverse path, it looks only at the negative axis. Okay, what happens to the past in the past of 0. And then you take the complex conjugate, okay, because you think about this Hermitian scalar product that you had at the beginning. And then this has to be positive. Okay, so this is a constraint on the law of the path. Very strange. It's not something you see in probability theory very often, but it comes from this line of reasoning we are making since this morning. And this is called reflection positivity, okay, of the law. Okay, so we can give a definition. A measure on path space, it's reflection positive if this holds for any cylinder function. Okay, these are the cylinder function supported on positive time. Just I don't want to give, unless you complain, I would not write down a precise definition, but please complain if you feel confused. I think the idea, but that's important, okay? You don't look at all the function on the path, you look at the function which looks at the positive times. And then this operation, you reflect and you take the complex conjugate, so the joining, so you see, you will have an Hilbert space structure, but the joint, the complex conjugate, it's where this is also doing a time reversion. Okay, very, very strange from a probabilistic point of view. And this is the condition you need. Okay, so our quest is, okay, we have an hope that to represent the Schwinger function with a stochastic process, but we need a stochastic process which satisfies this condition. And this is quite non-trivial condition already. Okay. Okay, you think a bit, and that's not easy to satisfy this condition. Okay, some symmetry really. Okay, what happens somehow? You think says between the past and the future of zero has to compensate in such a way that you get a positive number here. F is a arbitrary complex function. Okay, essentially. Okay, because you can approximate whatever you want here. Okay, now we want, okay, I will spend a bit of time to discuss what are these conditions and what we can do with that. So let's assume, okay, we want now to find process which satisfy this condition. Okay, essentially we know only two classes of process which satisfy this condition. They are either Markov processes or Gaussian processes. Actually, I think there are maybe Poisson processes, don't remember. Okay, but for continuous function, you rule out Poisson. Anyway, I know only two examples, okay? So what is the condition if you assume that is, let's assume that it's a Gaussian process. X is Gaussian and stationary. It's not difficult to see. So what happens, okay, then it has to be centered. And the covariance, so now I need to specify the covariance. So I need covariance is just given by function of time because you have time stationarity given by such that, if you want, maybe better. So what imply on the covariance? So it's not very clear if you do this, but okay, you impose this condition and then somehow you take some derivative. You see, for a general process, you cannot integrate unbounded function, but as soon as you assume that it's Gaussian, then of course here, if you can do this for this kind of function, you can do for any integrable, any function in L2 actually, okay? So you can allow to do it for the covariance, for example. Then if you do for the covariance, you see, okay, let me give an example, okay, what you see, okay, this function, of course, is not of this form, but I already told you, you can approximate and you, using the integrability in the Gaussian measure, you can make it work anyway. So this is positive. And you see this function, this is f of x. So what is theta of f of x? Well, you have to invert the times and you have to take the complex conjugate of the coefficients, okay? And then you expand and you see this relation, because then you have the correlation between one time and the opposite of another of these times, positive times. So for any ck, okay, these are ck in C and tk positive, okay? So this is the constraint you have on these parameters. So this is a condition on the covariance of the process. And okay, looks strange. Does not look very strange, because maybe it resembles the positive definiteness of covariances. If you would have a minus, then this would be like positive definite. But somehow there is a theorem. So function of this time are called totally monotone, which we don't care very much about, but okay, maybe it's interesting to you. What is more interesting is that total monotone function have a very nice representation. There is a theorem of Berstein, which says that any totally monotone function on R plus, they are defined only on positive times. As this representation, okay? So they can represent as the Laplace transform of a bounded positive measure on R plus, okay? The proof are on the lecture notes of the course, but I find, yeah, okay, just if you want to look at the proof, it's interesting. And okay, you can verify that if that's the case, you have really what you expect, okay? Because then if it's really sees this is this Laplace transform, then you can go back and check that this expression is exactly positive, okay? So provided provided we choose a covariance of this form, then we guarantee the positive definiteness. But Berstein theorem says even more, says that okay, the only example are of this form, okay, that you have really constraint. So the simplest, so let's look at the simpler example, okay? So what is the simpler example we can do to understand something about all this abstract setting is that take the measure in a single point, okay? That's the simplest example I could imagine. And what is the process, okay? So I take a point, alpha positive, because, okay, in zero there is not much interest, okay? There is nothing which change in time, so there is no dynamics, okay? If you take the measure concentrated in zero, this covariance is always one or a number. So it means that you are always one, that you have a Gaussian random variable which process which does not change in time. So you can take a point alpha positive and then take a delta concentrated in the point, then you get, of course, this behavior. So this is computed for positive time, but if you want the covariance for all time, you just take this, okay? Take absolute value. And you can choose the normalization constant, okay? Of course, you have a Gaussian process anyway, which will be reflection positive, but I choose just in this way, which is a convenient way to choose the constant. And this process has a name, of course. If you know probability, you recognize. So this is a Gaussian process in one dimension with this covariance is known, and it's called the Oster-Uhlenbeck process. Okay. And again, okay, then of course, if you have this, you can take linear combination. Okay, this formula tells you that, you see, what is telling you this formula is that any reflection positive process, Gaussian process, real valued it's a linear combination of Austin-Uhlenbeck process, okay? Because you can take independent linear combination of Austin-Uhlenbeck process, the covariance will be a linear combination, and then you can approximate any measure as you want in this way, okay? So at least you can approximate as finite linear combination. I think it's very interesting to think about it, okay, in this way. Okay, so this is this sets a point. So we start to see a concrete example, and I will try to develop the theory of this example, okay, today and maybe tomorrow. That's the goal so far. So we have elaborated our axiomatic framework in such a way that we arrived in somewhere where we have probability theory at end. And we have discovered that I can construct, so essentially what I'm saying right now is that you can construct Schwinger function from the Austin-Uhlenbeck process. And it would, I think it's interesting to see how you go back, so how the Austin-Uhlenbeck process corresponds, what is the quantum model which corresponds to this Austin-Uhlenbeck. What happens if I go back in my elaboration up to the quantum mechanical, what I will see then. Okay, I give you another, so that's our first example. So let me elaborate a bit more what reflection positivity, how much reflection positivity constraint our choice of model, okay? And another class of processes for which we can show reflection positivity is the class of symmetric Markov processes. So right now I'm just trying to explore, okay, the consequence of requiring the three property we require for a Schwinger function. Okay, so reflection positivity, these compatibility conditions, and the last analytic condition I would set aside, I would not discuss very much. But reflection positivity, it's already tricky, as you've seen. For essentially, if you look only at Gaussian process, I have only one example, which is Austin-Uhlenbeck process. If you look in a larger class of processes, maybe not Markov, that you look at symmetric Markov processes, so what is a symmetric Markov processes? Okay, so what does it mean, first of all, having a Markov process? So let's explore this strategy, okay, this Markovian strategy. So let X be a Markov process, okay? So far I said let X be Gaussian, now let X be a Markov process. So what does it mean? It means that, okay, being Markov, maybe I'm assuming that there are not only probabilists around. So maybe the analysts have seen this, but I just want to remind the definition in a very general setting. Okay, so Markov process means that if you take conditional probability of the future given the past, everything depends only on the present. Okay, so f of s is all the information which is you can acquire by looking at the process for all time up to time s. So this is the past and the up to time s. And then the conditional expectation is like the projection in L2 of the space of random variables, which are measurable with respect to the sigma algebras. Okay. And then you say that you have this reduction, okay, that somehow there is no influence of the past conditionally on the present. So this is Markov process. Okay, and why Markov process should play a role? Well, you remember that in the reflection positivity condition, while you have this distinction between somehow the past and the future, and you have reflection according to the time direction. Okay, so maybe we can make them play nicely. And indeed it happens while, okay, in this case, so if you recall what is the support condition of the reflection positivity, what can happen? Well, okay, let's look at what will happen. Okay, so if I have a reflection, okay, let's assume I take this function, which are supported only in positive times, and I try to compute this quantity. Okay, I want to prove that it's positive. So the first thing I can do is certainly to say, okay, this function is supported in the past of 0. Okay, so I can take, I will do it very slowly, but I think it's quite elementary. I can surely take the expectation of the condition expectation with respect to f0. And that's always, but in particular, now this function is supported in the negative time. Okay, so it's measurable with respect to this sigma algebra. And then I have this relation. Okay, and now these are used only support property. Okay, this is always true, but now I'm using Markov property, so I can replace this. This depends only on the past. I said somehow I can replace this by that, and you can do for 1 point, and then you prove by standard approach that you can do for any function which are measurable in the future. Okay, so this f is measurable in the future of time 0. So by Markov property depend only on the present. So here I use Markov property if you want. Okay. Okay, that's the key point. And then since this depends only on f0, then you can also apply the projection on the other part. Okay, then it comes for free that you can project the other part, and of course the expectation is real, so we go inside the conjugation, and then you have this situation. Okay, and then I want this quantity to be positive. Okay, so an easy way to force positivity, the condition for positivity, this quantity, is to assume that the law of x is symmetric with respect to time inversion. So what I mean that x is distributed like theta of x. Okay. In this case, essentially what you have, so I continue my elaboration here. So you have this, but somehow now you think a bit how you compute this, and you realize that actually, okay, you have to think a moment in this case, but essentially what you have is that let me think, now I'm a bit lost. Yeah, what you want to prove is essentially is, yeah, this property that that you have this property here, because then you can conclude just that. Okay, and this is positive because you just the absolute value of 1. So it's just this to the square. And I think this should be the case. So I wrote in my notes it's easily seen, but at this point I think I start to be a bit tired, and I don't see so simply. Yeah, so let's see what's... yeah, okay, yeah. it's easy to see, but okay, indeed. So let me finish today I think this is a good point to stop today, and let me just prove this. Okay, so for example, I'm not sure it's the easiest way to prove, but okay, one way to prove is that you just test with another, so this has to be G0 measurable, so you test with another G0 measurable function, and this has to have this form. So this is theta. Okay, let me write theta f of x. Let me actually, in all this consideration, should have written f of x, but I'm sorry. I forgot to write down. According to the notation I used, I should have used this kind of notation. But okay, so now, okay, I can remove the condition expectation because everything is fine. And then what is this? What does it mean? Means that I have take theta of that, but now you realize that theta of that, okay, but now you realize, yeah, that, okay, this is also theta of 0. This does not change, okay, because it's times 0. And now if you use the fact that the law is the same, you can remove this, okay, by symmetry of the law, by symmetry. So this is time invariance, symmetry. And now you go back, okay, now you condition with respect to gx0. Sorry, too many things. Now I want to condition f of x, yeah, see, it works, f of 0, and then you have gx0, and then you can identify for arbitrary g, so indeed, almost surely at least you have this, okay? Sorry, you have to use the Markov property if you want to get the final by Markov property. So here you get the Markov property. And you are done, okay? Yeah, so I was puzzled, but it's indeed the case. Okay, so let me stop here today. It's a good point to stop, I think. So before stopping recording, so let me make the point. So somehow we have discovered now what this computation show you that Markov process give you reflection positive probability measures on paths. Sorry, not all Markov process. They have to be symmetric with respect to time inversion, okay? So the law of x, so whether you look at the process forward in time or backward, you should see the same thing, and they have to be stationary. But provided you have this condition, somehow reflection positivity correspond to the Markov property, okay? So the point, so let me register this in a triangle point, saying, so what we discover is that stationary and time reversal invariant Markov process are reflection positive. And actually the converse is true in the sense that reflection positive Markov process are time reversal invariant and stationary. Okay, this is maybe I can leave you to prove. It's not difficult. Okay, so let me stop here. We are in a good position. I think tomorrow I will try to wrap up all this discussion of the relation with quantum mechanics, try to work out a full example, which is the harmonic oscillator, and motivate what will go on, that is how you construct example of quantum mechanics with infinitely many degrees of freedom. Okay, that's our goal. So we somehow try to work out in detail 1 degree of freedom, and then we will jump to infinitely many. Okay, so, but I think these examples show, we will essentially tomorrow, what we will going to do is that take the Gaussian, the Oster-Uhlenbeck process, and work out what is the quantum mechanics associated to the Oster-Uhlenbeck process, and then try to perturb around this to find other interesting models. And this will motivate what will be the object which will occupy us in the rest of the week and next week. So I stop here for the moment.